Welcome back to Étale cohomology on December 15th, 2020. So today is our final kind of bonus class. So the plan today is to sketch the remainder of the proof of the Riemann hypothesis. So I'll sort of recall the plan from earlier when I sketched this before, and then indicate what needs to be done to fill in the gaps. And then we'll talk about I'll kind of give a statement of the main theorem in Weil II and some applications of that. And also of Weil I itself. So let me remind you what the strategy for the proof of the Riemann hypothesis was. So we reduced to the following claim. So we reduced to the situation where X is even dimensional. Of dimension n+1, and we wanted to prove some inequality for the eigenvalues of Frobenius on the middle cohomology of X. So we want that the eigenvalues, let's say alpha of Frobenius, acting on the middle cohomology, so that's the cohomology in degree equal to the dimension, satisfy some inequality. And that inequality was that q to the n over 2 is less than or equal to the absolute value of alpha is less than or equal to q to the n over 2 plus 1. So the Riemann hypothesis says that for any embedding of the field generated by alpha over q into the complex numbers, the absolute value is q to the n over 2 plus 1/2. So here this inequality is wrong by an error of a factor of q to the 1/2 in either direction. And then there was some tensor product trick argument to reduce the statement of the Riemann hypothesis, to reduce the proof of the Riemann hypothesis to this case. Then, okay, so the idea was to do some, so the proof was some induction on n. So step one was to find an embedding x into Pn, some big N, such that there exists a Lefschetz pencil L. So let me remind you, over an algebraically closed field, one can do this by taking any very ample line bundle on X, embedding using it, and then maybe replacing it with its square. And then we said that for an arbitrary smooth projective variety, the square of very ample always admits a Lefschetz pencil over an algebraically closed field. All right, so we're not actually over an algebraically closed field, we're over a finite field. And so the sort of genericity arguments or the Bertini argument that go into proving that theorem doesn't quite work. But this statement is insensitive to extending the ground field. So what you do is you just find a Lefschetz pencil over your algebraically closed field, and then descend to, then maybe extend your ground field. So it's defined over that base field. And Jose asks, are you all seeing what he is writing? So I stopped writing after such that there exists a Lefschetz pencil L. So does everyone see that? Okay, great. Okay, so then step two. So sorry, I was just sort of. I mean, this is sort of not the interesting part of the argument. So I was just sketching it verbally. All right. So step two is it's enough to show the theorem. The theorem for the blow up along the base locus of L at X. And this is just by computing its cohomology. So because the cohomology of X injects into the cohomology of this blow-up. we're just going to replace. So we'll replace X with the blow up. Okay, so now given this, we have a Lefschetz fibration. So we have this map blow up of X to P1, which I'll call pi, which is a Lefschetz pencil, Lefschetz fibration. And we want to understand Hn plus 1 of Hn plus 1 of this blow up. So the Lorac spectral sequence gives us a way of computing that. So it says we get Hi of P1 with coefficients in Rj pi lower star of QL, and this will converge to Hi plus j of the blow up of X QL. Okay, so there are going to be three interesting cohomology groups here to study. So the three interesting cohomology groups, so the interesting groups are going to be, first of all, H2 of P1 with coefficients in Rn minus 1 pi lower star QL. 2 will be H1 of P1 with coefficients in Rn pi lower star, sorry, this is just an Rn pi lower star QL. And then finally, H0 of P1 with coefficients in Rn plus 1 pi lower star QL. Okay, so when I say these are the three interesting groups, I just mean these are the groups that are contributing to the cohomology we're interested in, namely Hn plus 1 of the blow up. Are there any questions so far? All right, if not, let's keep going. So let's see what happens in each case. So namely, we just want to show the same inequality for the eigenvalues of Frobenius acting on these groups that we wanted before. So in particular, we want to show that those eigenvalues for any embedding of the field that generated over Q into C have absolute value between Q to the n over 2 and Q to the n over 2 plus 1. All right, so now we have to use some facts from the theory of Lefschetz pencils. So the main observation is that this sheaf is actually constant. So this is something that follows from the fact that the singularities that show up in a Lefschetz pencil don't contribute to cohomology except in the middle degree. So this is not so. This is so once we know that, well, what is this? This is just going to be H2 of P1 with coefficients in, well, it'll just be a kind of constant sheaf. So that constant sheaf will be like Hn minus 1 of a fiber. And I'll underline it to give you a constant sheaf. Okay, and what is this? This is just Hn minus 1 of the fiber twisted by minus 1. All right, so does anyone see what to do from here? So we're now going to use the induction hypothesis. So the fiber is a variety of odd dimension n, but we're just going to slice it one more time. So taking a hyperplane section, let's call it Z, we get a map from Hn minus 1 of the fiber. And now by the weak Lefschetz theorem, this map is injective into Hn minus 1 of Z. And this is the middle cohomology of an even dimensional variety. So we're done by the induction hypothesis. Are there any questions about that step? So the geometric content here is the weak Lefschetz theorem, which tells you that if you look at cohomology below the middle degree, when you restrict to a hyperplane section, you get an injection. So this is a statement I never proved, actually. I told you the statement earlier on, but the proof involves a lot of Galois cohomology, which would have taken us too far afield. I think Ben asked about it, but I think it's a little bit too much to do in the time we have remaining. All right, so let's do part 3 next. So part 3 is more or less the same. So that was H0 of Rn plus 1 pi lower star QL. So again, in good situations, this is a constant sheaf. So this is the good. What I mean by good situation is if the fibers of your Lefschetz fibration are irreducible, which you can arrange. So this is a constant sheaf in good situations. And well, then the same argument works. So the same argument plus Poincare duality. Okay, so the interesting case is part 2, which is H1 of P1 with coefficients in Rn pi lower star QL. Okay, so this is the sheaf. This Rn pi lower star QL is the sheaf that we studied in terms of vanishing cycles when we were trying to understand Lefschetz vibrations. So we defined inside of this a subspace E, which was spanned by vanishing cycles. So this was the span of the so-called delta S, so the vanishing cycles. We argued that this vector space had a skew symmetric product on it, and inside of E we had E intersect its orthogonal complement under this product, and then inside of that we had 0. Okay, so we're just going to study 3 pieces. So we're going to study H1 of this is E is not inside of this H1. It's inside of, sorry, let me rewrite this to be a little bit more clear. So inside of Rn pi lower star QL, we had a subsheaf E. And then inside of that, we had E intersect its orthogonal complement. All right, so we're going to study sort of the 3 associated graded pieces. So we're going to study, so this is going to be kind of 2. Part A will be, we're going to understand Rn pi lower star QL mod E.
Wait, did the inclusions go the other way? I'm a little confused.
Yeah, the inclusions go the other way. Sorry about that. Yeah. We're going to study E mod E intersect E orthogonal complement. And then C, we're going to study just E intersect E orthogonal complement. So the sort of content of most of what we did at the end of last time was to check that this satisfies the hypotheses of the main lemma. And one of the consequences of the main lemma was that we win in that case. So in that case we win, namely H1 of P1 of E mod E intersect E orthogonal complement satisfies the inequality. All right, so there's these 2 remaining pieces to understand. Can anyone help me out? So the claim is that Rn pi lower star E QL mod E and E intersect its orthogonal complement are constant sheaves. So does anyone see why this is the case? So the proof is the Picard-Lefschetz formula. So for Rn pi lower star QL, let's remind ourselves, so how does sigma act on some element x? It sends it to x plus or minus, well, some character of applied to sigma times x cup delta s. Okay, but this lives in E. So that tells us an element of inertia acts trivially on this quotient, because all it would do is, to given an element to it, it would add something. Sorry, this is some sigma s in an inertia group. So all it would do is add something in the thing you've quotiented out. So for E intersect E orthogonal complement, well, this cup product x cup delta s is just identically 0 for all s, just because we're, that being in the orthogonal complement means this cup product is 0. Okay, and now given this fact, we're again done by Lefschetz. So there's a little bit to check, but it's not so hard. You just have to analyze these two pieces separately. All right, so that, I claim, finishes the proof of the Riemann hypothesis. Sorry, go ahead, Ben.
I was just wondering, so this formula works for anything in an inertia group, right?
Yeah, and then the claim, which is proven by reduction to characteristic 0, in fact, is that the inertia elements generate pi 1.
Right, okay, I see. But you have to take the inertia at more than one point, right?
That's right. So this S here, the sigma S is a point.
Okay.
The inertia at a point in the base.
Right.
But this is true for the in the base. So
morally, what you're doing is you're taking like you're proving this at each of the inertia and then at each of the points. And then if it has, because this r pi lower star thing mod E has 0 action at each of the inertia points, then that tells you that it's actually constant everywhere.
That the whole pi 1 action is in fact trivial. That's right.
Okay.
Yeah, that's it's really an amazing fact. So yeah, what you should think is that P1 minus a bunch of points is like a sphere minus a bunch of points. And so its fundamental group is free on the loops around all but one of the points. And the proof is actually what you do is you lift a characteristic 0, you use the surjectivity of the specialization map on the tame fundamental group, and then the topological fact that inertia generates pi 1 in characteristic 0. So in some sense, the proof of the Weil conjectures has some analytic input from complex geometry. And in fact, I mean, so this fact that pi 1 of P1 minus a bunch of points is, at least the tame part of it, is free. There's no known algebraic proof of that. It's kind of a shocking fact.
Okay, thanks. Wait, actually, sorry. Do we know it's actually free or just a quotient of a thing generated by those things?
Yeah. So oh, sorry. The tame fundamental group, I think, is not. Well, let me think about it. Yeah, I think it's the tame fundamental group is not free. The prime to P fundamental group is a free prime to P group.
Okay, thanks.
Sorry about that. Yeah, that's a good point. All right. So now what I want to do is I want to tell you a little bit about Weil II and give you some applications. So here's so let me talk about Weil II and some applications. And if we had more time, I was kind of actually hoping to do like a sort of whole second half of the course on this, because I think this stuff it's very useful to know what you can do with this stuff. But we have one day, and my plan is to have a bunch of office hours just sort of open to everyone next semester, so we can discuss it more then too. Okay, so here's the theorem of Deligne. So this is a sort of special case of Weil II, but it's illustrative. And it's the sort of main input. So let's suppose U is a curve, is a smooth geometrically connected curve, maybe not proper. And I'll suppose F is a QL sheaf on U, which is pure of weight 0. So here, pure of weight 0 means that the Frobenius action on the stalks. So what this means, let me maybe actually write this down. What this means is that fx, the Frobenius acting on the stalk of f at a point x, has eigenvalues alpha such that the absolute value of alpha is just 1. Meaning, for any embedding of the field generated over Q by these eigenvalues, you just get 1. So such a thing will basically never show up as the cohomology of an algebraic variety, but you can always, I mean, if you, for example, if you take an abelian scheme over U, its H1 or R1 pi lower star will be a something with weight 1. The eigenvalues of alpha on the fibers will be Q to the 1/2. But you can just kind of twist by a character of the absolute Galois group of the ground field to get yourself into weight 0. So it somehow doesn't really matter that like you can always twist a sheaf that sort of is coming from a smooth projective variety to satisfy this condition. So then the theorem is that H1 with compact support of U is changed to FQ bar with coefficients in F is mixed, and I'll say what this means, of weights less than or equal to 1. Okay, so what this means, so what is mixed of weights less than or equal to 1 mean? So this means that the eigenvalues of Frobenius alpha of Frobenius satisfy alpha is Q to the I over 2, where I is in Z less than or equal to -1. Sorry, greater than or equal to -1. Sorry about that. Okay, and then the corollary, which is just immediate by Poincare duality, is as follows. So just without compact support, H1 of UFQ bar with coefficients in F is mixed of weights greater than or equal to 1. And in fact, it'll just have weights I mean, combining these facts, you really are just going to get weights which are for, in the second case, it'll just be weights 1 and 2. That's all that will happen. All right. Are there any questions about this?
Do we want it to be pure and mixed with respect to just some embedding of QL bar into C, or?
Yeah, so there's 2 statements. You could say, you could define an iota pure and an iota mixed sheaf, and the statement would be true in that setting, but we really only care about the case of pure and mixed, which means for all embeddings. Yeah, so Deligne does make sense of this notion of an iota pure and an iota mixed sheaf, so that's relative to a single embedding, but it's not, I mean, that as far as I know, that notion of being pure or mixed relative to a single embedding never really comes up.
What is Z iota -1?
Oh, sorry, it just means integers which are at least, oh, that's not an iota, sorry, that's greater than or equal to -1. Let me clarify that. So it's just the integers which are at least -1.
Is it clear why you have these weights spaced out like this? Like the bounds, I think.
What do you mean by spaced out like this?
Like where the weights are sitting in Z greater than or equal to -1. Like I think in Katz's proof, he just shows the bound, but he doesn't show. I think there's an extra monodromy argument you have to do to get them spaced out like this.
I don't understand what spaced out means.
No.
Do you mean why are they half integer?
Yeah, why are they always half integers?
No, that's a huge part of the proof.
Oh, right.
That's a big part of the content.
Okay, great.
Yeah. Yeah, no, that's definitely not clear. That's the hard part.
Okay, great.
Yeah. Okay, so already, I mean, so just the fact that these are so for example, in this case, just the fact that these so one thing this says is that these eigenvalues can't have absolute value 1 in this corollary, right? And so in particular, they can't be 1. And already that it gives you a huge amount of information. So let me give you an application, a sort of very simple application of this. So application. So suppose x to u is a smooth proper morphism. Of varieties over a field K. So then one gets so then for each I, one gets a representation rho I from pi1 of u base change to k bar. So this is the Étale pi1. Maybe let me pick a base point, some little u, into GL of, so this is like the monodromy representation on the cohomology of the fibers of this map. So I'll take the ith push forward and look at the representation on the fiber over u. So because this is a smooth proper morphism, this push forward is a locally constant QL sheaf by the smooth and proper base change theorem, and the data of a QL sheaf is the same as the data of a locally constant QL sheaf is the same as the data of a representation like this. Okay, so the theorem of Deligne, which is going to be a consequence of Weil II, is that these representations rho I are semi-simple. Okay, and okay, what does that mean? It just means they're a direct sum of irreducibles. So if you have any sub, it has a complement. And that's a very strong statement. Like for example, if U is an open sub scheme of P1, its fundamental group, let's say if you're over an algebraically closed field of characteristic 0, is a free profinite group. And it's very easy to write down representations of free profinite groups, which are not semi-simple. Like you just, for example, if you have a free group on one generator, like Z hat, you can take the representation 1x01. That's not a semi-simple representation. So this is saying that such representations can never show up from the cohomology of smooth projective varieties. Are there any questions about the statement?
If you drop the smoothness, are there counterexamples?
Yeah. So it's not true for non-proper varieties. What's going to happen is that these local systems will have a weight filtration on them, which is it's just some kind of canonical filtration. And if you take the associated graded pieces of the weight filtration, those will be semi-simple. But there can be interesting extensions between the different weight pieces. And just as an example, I mean, so Edward Luyenga gave a very nice talk at UGA a couple weeks ago, which maybe some people here saw, where he what he did is he computed the action of the fundamental group of MG on the configuration space of like 3 points on a curve, and showed that representation is not semi-simple. So it's not very, and basically if you take a random family of non-smooth or non-projective varieties, non-proper varieties, you wouldn't really expect the cohomology, the representation to be semi-simple. Any other questions about the statement here? Okay, so I'll sketch the proof. So step one is to reduce to the case of finite fields. So the data here, pi, x, and u, are all defined over some finitely generated field, or even some finitely generated Z algebra. Well, why is this? This is like my favorite trick in all of algebraic geometry. You have a variety. It's defined by a finite collection of polynomial equations. those equations have finitely many coefficients, maybe like 3 and 7 and pi and e and the Euler mesh or an e constant or whatever, and you can just adjoin those to Z. And then you get this picture over Z. So you have a map X to U over Z. Maybe it won't be smooth and proper anymore, but those conditions are constructible. So you can just delete some stuff to make it true again. Okay, and now you can specialize to a finite field. So there's a little bit of subtlety in the specialization, but it's not so hard to deal with. So this is, we're using more or less the surjectivity of the specialization map on the prime to P fundamental group. Okay, so now what do we have? So let's let E inside of Ri pi lower star QL be a locally constant subsheaf. And we want to show, it has a complement. So we want the corresponding element. So we get an extension. So in other words, we get an extension 0 to E to Ri pi lower star QL to the quotient, which I'll just call F, maybe 0. We want this to split. Okay, so this extension is given by, so let's call this extension star. So this star lives inside of X1 pi 1 étale of UFQ bar. So these are the extensions of representations, F comma E. Okay, but in fact, it lives inside of a subspace of this. Does anyone see what kind of subspace it lives in? So one might have to replace your field with a finite extension, but because this extent, so if you just think about what these representations can look like, the fact that this extension actually occurs over your ground field means that this lives inside of the Frobenius invariance inside of this group. So this is the Frobenius invariance. So the goal, yeah. So the point is that you can descend this extension to a finitely generated, to a finite extension of your finite field. So maybe this is after replacing K with a finite extension. So our goal now is to show that X1 pi 1 étale UFQ bar E F E. Oh no, there's two Fs. This is Frobenius. Frobenius fixed is 0. So in other words, there's no Frobenius equivariant extensions like this. Well, what is this group? This is the same as H1 pi 1 étale U FQ bar with coefficients in Hom FE and then Frobenius fixed. Well, this is the same as H1 of U FQ bar étale with coefficients in Hom. Maybe let me make it clear these are inner Homs, FE, Frobenius fixed. All right, does anyone see how to finish the proof from here?
So you would expect that Hom FE to be weight 0?
Yeah, that's exactly right. So F and E have the same weight.
Yeah.
Because they're
Actually, I have a question about this.
Yeah.
Are we assuming after we reduce to FP that it's still smooth?
Yeah, so you can, that's absolutely right. So you do that by spreading out and then choosing a prime where it's still smooth. And smoothness is an
Okay, I
open
see.
condition. So
Right. Okay, so we're not doing this for every prime. We're doing it.
that's right. We're just using one prime. In fact, I mean, somehow these arguments, they almost always use only one prime. It's very hard to see, like different Frobinii, we don't really understand, I think, how they talk to each other. Yeah,
Okay.
I think that's actually a general principle, which is that if you have a plan to prove something by using more than one prime, it's always going to be a little bit deeper. And in this case, I think Weil II is quite deep, but you know, this is the sort of situation where, yeah, this is the kind of thing where you're typically going to use only one prime. At least that's the principle I think is accurate. Yeah, so these two sheaves have the same weight just because they're subquotients of Ri pi lower star QL. So here we use the Weil conjectures. So by the Weil conjectures. So namely, like, how do you compute the weight of such a thing? Well, the fibers of this are just the cohomology of the fibers of our map. So that's the cohomology of a smooth proper variety. So it has weight, weight I. So F and E both have weight I. So this implies that Hom Fe has weight 0. Because what is it? It's like F dual tensor E, and so the eigenvalues are like something of absolute value q to the minus I over 2 times something of absolute value q to the I over 2. So that has absolute value 1, which is what it means to have weight 0. So this implies by Weil II that H1 of U FQ bar with coefficients in Hom Fe is mixed of weights. Well, I'll just say what they are. So the weights are 1, 2. So strictly speaking, all I stated was that the weights are at least 1, which is also all we need. But in fact, it's true that it's mixed of weights 1, 2. Okay, and now we're done. So this implies that 1 is not an eigenvalue of Frobenius, which implies immediately that the fixed points of Frobenius acting on this vector space are 0. And that's what we wanted to show. So this is already, I think this is a really amazing theorem. So for example, this statement that we just proved, that these rho I are semi-simple, is true over the complex numbers also. And we proved it by reduction to characteristic P. So you could also prove that statement over the complex numbers Hodge theoretically. So there's a sort of analog of Weil II for variations of a Hodge structure, or really mixed Hodge modules. And so one could also give a proof that way, and it would be somehow more or less the same proof. All right, are there any questions about that? All right, so maybe let's take a 2-minute break. I'll grab some water, and then we'll do Chebotarev density. All right, if you guys are cool with that, I will be right back and grab some water. All right, I'm back. So any questions before we start talking about Chebotarev density?
Does this whole thing of like Deline's equidistribution theorems following from this semi-simplicity?
I don't think it, I wouldn't say it follows from semi-simplicity. I mean, it's kind of a beefed up version of Chebotarev density.
Ah, I see.
Yeah, so let's talk about Chebotarev. So I guess this is application 2. So this is a sort of version of Chebotarev for varieties of over finite fields. There's a version for kind of finitely generated Z schemes even. So a special case of that is varieties over a finite field. Varieties over a finite field are finite type Z schemes. But you need a little bit more analytic number theory to do that case. So I'm not going to do it. That said, I do think, I mean, even if you look at the classical Chebotarev density theorem for number fields, you can see somehow the same proof is happening as the one I'm about to sketch. So I find this point of view extremely illuminating. Okay, so here's the theorem. So I think this was maybe observed by Serre. So Serre, I think, did this using you can do this just using the Langbae estimates. If you're very careful, we'll see that one gets much better error terms using the Bay conjectures. So I consider this an application. So suppose X is normal, and F Y to X is a G cover, and here X and Y are geometrically connected. Schemes over finite field F cube varieties. Okay, so let me just say a word about what I mean by G cover. So what I mean is that F Y to X is finite étale with Gala group G. So in other words, it corresponds to a surjective homomorphism from pi1 of X to G. So let C inside of G be a conjugacy class. So then the theorem is that if you look at the proportion, so the number of X in X FQ to the N, such that the Frobenius at X, so let me remind you, if X is a rational point of big X, so it's the same as a map from spec FQ to the N to X, and that induces a map on fundamental groups. So you get a map from the Galois group of FQ to the N to the fundamental group of X, and the image of Frobenius is well defined up to conjugacy. So that's an element called Frob X inside of pi1. So if you look at the, so that maps to pi1, maybe let me give some notation here. So here, F corresponds to some map pi1 étale X to G, and I'll call that map rho. So this is sort of the deck transformation action of pi1 on Y. So we can ask for the probability of Frobenius will land inside of C, inside of this conjugacy class. That makes sense because Frobenius is well defined up to conjugacy. And so we can look at this probability as if you just choose so we'll divide this by the number of rational points of X. So the statement is that this tends to C over G as n goes to infinity, and in fact we'll see from the proof that you get pretty explicit error terms, and then we'll see the explicit error terms. And those error terms will capture something about the geometry of X, which is why I'm saving them for the proof. All right, are there any questions about what this statement says? So basically, another way of thinking about this is if you pick a point, you get the Frobenius at that point, and you can ask how is it acting on the fiber, And this is saying you can compute the probability that it will act via a certain conjugacy class of the deck transformation group. So are there any questions about this statement? And it's really, I mean, if you replaced X with spec of the ring of integers of a number field, this would really be the same statement as the classical Chebotarev density theorem, maybe again minus some kind of error term.
So, sorry, how does the map row work exactly? I'm just a tiny bit confused.
Yeah. So what is a G cover? A G cover is the same as it's a finite Étale X scheme with covering group G. And my claim is that so remember that we had just the definition of pi 1.
Can I ask a clarifying question about that? So
yeah, go ahead.
A G cover has to be like Galois, right?
Yeah, that's what I mean.
Okay. So because I was just like thinking for a second, if the cover wasn't Galois, then you wouldn't get a map from the full pi 1, right?
You'd still get a map. So yeah. So what is? Let me just say what is a. Let's remind ourselves what is the correspondence. So a finite Étale X scheme is the same as a finite set with an action of pi 1. So for example, that's the same as a map from pi 1 to a finite symmetric group, right?
Okay.
And then you could say, well, G is the image, and then G is acting on some finite set. The fact that this is Galois just means that that finite set is G itself, and it's acting via left multiplication.
Okay.
Yeah. Cool. Any other questions? All right, so let's look at what we're trying to count. So let's let 1 sub C from, let's say, from G to QL be the indicator function of the conjugacy class C. And what do we want to do? We want to count sum over the rational points of 1 sub C of rho of the Frobenius at X. This is the kind of thing we're interested in. So this is precisely the numerator of this fraction here. Do you guys agree with this? So this looks like the kind of thing we could approach via the Lefschetz trace formula, right? So if in particular, if this was, instead of 1 sub C, if this was the trace of Frobenius acting on the stalk of some sheaf, then this is the kind of thing we'd be able to access using the techniques we have, like the Lefschetz trace formula for local systems. So the idea is, well, we should use this is one basis of functions on G. There's another basis which looks more like sheaves, namely the basis of characters. So the idea is we want to write this as the sum over X in XFQ to the n of some AI times the character, or sorry, this should be another sum over chi I, a character of G, of some AI times chi I of rho frob X. So we'll figure out. Well, let's actually do that first, and then we'll rewrite this in terms of sheaves. So can anyone tell me what should the coefficient of AI, what should the coefficient of a character here be? Like, how do you rewrite the indicator function of a conjugacy class in terms of characters of a group? So like, how do you compute this AI?
Well, you could apply the characters and do some summing and orthogonality relations.
Yeah. So can anyone remind me what to do? What exactly is the formula you get?
Should be the sum overall of characters, like divided by the size of the group.
Yeah. So I think you get 1 over G times the sum of x in x f q to the n times, I think you end up getting chi of the conjugacy class C times chi of rho from x. Do you guys agree with this? Oh, sorry, there should be another sum. I keep missing the sum over characters. So I think this is what you got. I mean, how do you pair, sorry. There should be there should be a size of C here also. Yeah. How do you pair a character with a conjugacy class? You just evaluate the character on the conjugacy class and then sum over the elements, right? I think maybe that's what you were saying, Ben.
Yeah, I think I was answering a different question, but yes, I agree.
Yeah, okay. So let me factor out that C. So you get C over G, that's looking good. Sum over X in X F Q to the N. Sum over characters of chi I C times chi I of rho of frob X. Okay, so now we need to interpret this sheaf theoretically. So this is sort of the beginning of the sheaf function dictionary, which is one of the reasons I wanted to explain this. So what is this? So given chi I claim we get a sheaf, and how do we do that? Well, we have our representation rho from the fundamental group of X. This goes to G, and then what is chi I? So chi I is let me call it, well, chi is the character, so that's the trace of a representation. So if there's a representation rho chi I to GL Ni of QL. So let's call the associated sheaf, let's call it F sub chi I. And if you just unwind definitions, this chi I of rho of frob X is precisely the trace of the Frobenius at X acting on the fiber of F chi I at X. And why is that? Well, what is chi I? It's just the trace of rho chi I. I mean, that's how you go from a representation to a character. So in other words, the sum from before it becomes C over G times the sum. I'm going to switch the summations. So sum of chi I in the characters of G, sum of X in X F Q to the N of the trace. Sorry, there should be a chi I of C here. So this is some constant times the trace of the Frobenius at X on this F chi I at X. Okay, so what do we want to show? Can anyone tell me? So we're trying to compare this thing divided by this to C over G. So in other words, we want to show that this is, as n gets big, this is kind of on the same order of magnitude as just the number of rational points of X. So that's namely the cohomology of the trivial sheaf. Yeah, so let's rewrite this. So we can use the Lefschetz trace formula to rewrite this as follows. This is the sum. This is the sum over chi I in the characters of G of the sum from I equals 0 to 2 dim X of -1 to the I times the trace of Frobenius on the compactly supported cohomology of X, F Q bar, with coefficients in the sheaf associated to chi I. So this is what we're trying to, oh, and I missed I missed this chi I of C here. So this is what we're trying to understand. All right, so can anyone tell me what does this look like? So these sheaves are of weight 0, right? So now this is something we can understand. So there's two possibilities. So first of all, we can take chi I to be trivial. So that shows up once, the trivial character shows up once. So that sum n becomes just sum I equals 0 to 2 dim x of the trace of Frobenius on the cohomology of x. Okay, so this is actually what we're trying to compare the sum into, right? This is just equal to, here, there should be a from to the n everywhere because we're looking over fq to the n. So this is just the number of points on fq to the n. So we want to show that everything else is small, right? So the other situation is we want to show chi I is, if it's non-trivial, we want that the sum I equals 0 to 2 dim x of the trace of Frob to the n on the compactly supported cohomology of x with coefficients in the associated sheaf, we want this to be small. Meaning we want it to be dominated by this number. So small here means, let me give this number, let me call it n sub, let me call it, so let me call this number like, like t of n comma chi. So it's something that depends on n and chi. And we want that t n chi divided by the number of rational points tends to 0 as n goes to infinity. And so these will be precisely our error term. So we want to bound this number. Does anyone see how to do this? So what if x is a curve? Maybe that's the easy case.
Why do the f at chi have weight 0?
Yeah, because I mean, so what is the image of this representation? So f chi is the sheaf corresponding to this representation, but this representation is finite image because it factors through a finite group G. So what that means is for any Frobenius, it goes to something finite order in GLN, and the eigenvalues of something of finite order are infinity.
Right. Okay, I see.
Yeah. So the point here is that let's look at these cohomology groups. So H0 with compact support of x fq bar f chi I is going to be 0 because the chi I are non-trivial irreducibles. Sorry, that's not the interesting one. Sorry, the interesting one is 2 dim x. So this is 2 dim x. So this is going to be dual. This is dual to H0 of x fq bar f chi I guess dual twisted by the dimension, and this is equal to 0 because the chi I's are non-trivial irreducibles. They have no fixed part. Right. So this piece is precisely the fixed part of the fixed part of the representation. So what that means is that we get contributions to the sum Tn chi from Hi with compact support xfq bar f chi I for I strictly less than twice the dimension of x. Okay, and now this Weil II theorem. So the interesting part, for example, if your curve is H1, what this says is that the eigenvalues of Frobenius have absolute value q to the I over 2 for I less than twice the dimension of x. Which means that the sum, so the sum T, so here I'm using a kind of slightly fancier version of Weil II than the one I stated. So I'm using it for arbitrary normal varieties, which is a little bit more involved. But you can deduce it from the one for curves. I mean, if you were a little bit more careful, you could actually avoid using any Weil II at all and just use Weil I here. So what this tells you, though, is that this is at most q to the 2 dim x minus 1 over 2. So that's the biggest the eigenvalues can be, times the sum of the Betty numbers. So the sum of the dimensions of Hi at compact support is FQ bar XFQ bar, sorry, F chi I. Okay, and this is some absolute constant. Sorry, and there should be an n here. Yeah, and there should be an n here also. Sorry about that. So what am I saying here? I'm saying that computing the traces, well, you can bound that by bounding the eigenvalues, which Weil II does, and then bounding the number of eigenvalues, which is just given by this dimension. This dimension is independent of n, and this grows like something that grows, it grows like q to the 2 dim x minus 1 over 2 to the n. So what this implies is that t over n chi divided by q to the dim x goes to, sorry, q times n goes to 0 as n goes to infinity. And this is what we wanted to prove. So this is so the number of rational points xf q to the n grows like this, grows like q to the dim x to the n. So that follows, for example, by Weil I or just by the length Bay estimates. All right, so that completes the proof. Sorry, it was a little messy. But let me just make some remarks. So what happened to the error term? So the error term is just this. It's really this Tn chi divided by xf q to the n, and we bounded it. So we bounded it by something like q to the dimension minus, this is q to the dimension minus 1/2 times n. And then there's a constant factor coming from the Betty numbers of the variety. So that tells you that the geometry, so like the Betty numbers, actually influences the error term in Chebotarev density. And I think with this in hand, it's really fun, I think, to go back to the usual proof of Chebotarev density for extensions of number fields and see somehow that all the same techniques are actually showing up. All right, are there any questions about this? So maybe there's a softer remark, which is that this actually just gives, I mean, I say that so number xf q to, so sort of softer version of this is I said that the number of points of f q to the n, xf q to the n grows like, q to the n times the dimension of x. So that's Lang Wei. So what is the error term? So what this tells us is that the error term is something of the form q to the n times, sorry, yeah, q to the n times dim x minus 1/2 times the Betty numbers. So the total Betty numbers, for example. So this is the exact same argument, just using the Riemann hypothesis. Cool. Yeah, so this is a sort of softer version of what we just did. All right, so I don't think we have time to do the other application I had in mind, which is formality. So maybe let me stop recording now, and then I'll hang around for a few minutes in case y'all have any questions or just want to chat. And thank you guys so much for coming to this class, and I hope it was fun and valuable for you.
Thank you so much.